Okay, so today we will start this new topic on structural modeling analysis. I want to divide this discussion into two parts. One is the conceptual, which we will do now, and then next one will be the practical application in ETABS. So I don't want to mix them together because I think it's very important to clear what we are doing and why we are doing it, and then how we are doing it will be done together, mostly after midterm in ETABS sessions. So details on how will not be discussed so much. The question, and the reason now, as I told you, these days with AI and all of that stuff, the question of how is very clear now. It's not a problem. You can find most of things in 1 minute without any difficulty. So the question of why is still important. So that's the part that we will discuss. So fundamentals of structural analysis, and basically we'll go back to the idea of why we are doing this. And then we will come to some of the important application of analysis. And then finally, when we go to the ETABS training sessions, we will talk about how to do that. Okay, if you remember, we do this equation many times, and this is the equation of why. Why we need to do anything that we do is about prevention of disaster. And we have seen this before. I want to go it quickly. And primarily, we are looking at this one, reducing the vulnerability, as you know, of the structural systems. And we continue to talk about this one. And now we keep going up and up and up. Previously, we talk about vulnerability as ductility and those kind of things. Now we are saying, okay, how do we start at the big picture until we come back to this one? And how can we really relate this to at this top level? So we talked about already, nonlinear analysis, modeling and all that stuff, but we didn't talk about how that connects to the top. We already discussed the key performance indicators, and we need to remember that now we need to compute them, all of them. How do we compute them? We compute them through analysis. And so all of those need to be now computed one by one for your project. Once you have done the system selection, you have talked about a lot of systems and how to select them, which is good, which is not good. Now the question is, how do we calculate all these things for our purpose? And once again, we have three loads: gravity, wind, and earthquake. Gravity, we already discussed that it is stiffness-based distribution, is easier. Most of the loads are rather static most of the time, so especially in buildings. So you can do a normal analysis, even hand calculation, bending moment can be calculated, tables can be used. So it's not that complicated. But the lateral loads are very, very, very important, and they are complicated because of their nature. And we talked about that the wind load and earthquake loads are very different in nature. This one is a load, and that one is a displacement. So we now have to come back to how are we going to handle them in analysis. So we are going upwards, and that equation I showed you earlier, this equation, we need to get back to this equation now and try to understand how this equation actually is developed first and how it will be used. So so this one we already saw. We need to now talk about all of that. Linear, non-linear, this one, earthquake demand, how did we get here? How do we analyze? How do we calculate the displacements? How we calculate the force? How do we reduce it? How much factor we will do? So all of those details that we have seen before, now we need to get down to calculating them. And we also have to climb this ladder, intuitive design, all the way to resilience design, consequence design, performance-based design, and we will see what equations do we need to do all of that. What is the difference? Where do we stop, and why we stop the wind here, and why we need to go for earthquake all the way, and what will take us all the way? So that's the purpose of this analysis part first, and then we will come back to the modeling part. Okay, so you have already seen these diagrams, but I'm just reminding you. So let's go back to the beginning. Once again, I'm not so sure if you have seen these slides. Maybe you have, maybe you haven't, but knowing everyone, you have probably forgotten. So let's go again from the beginning. So you remember this one, Galileo, right? Yes? No? Okay. You remember him? You remember Hooke, and you remember Newton, and you remember Young. So these are the four people that we must never forget, because they are the one who started this whole story, which is still very much what they started. Okay, so they are the key four figures from history, and we will pick two of them now. First, we will pick Newton and we will pick Hooke and see what they have done. So that is Newton, as you know, physics, high school physics. Did you really understood what it means when you read this one at that time? What does it mean, this equation, F is equal to m dot acceleration or u double dot? Can someone explain to me, because I want to, because you have done Professor Penning's course and everything, how do you really understand this equation? Who will explain to me? What does this equation stand for? The thing is, it's saying that if there is a mass sitting here, and if you want to start making it move at a certain acceleration, you need to apply a force. And the amount of force that you need to apply depends on how much acceleration you want to achieve. So basically, this is the force needed to accelerate a mass to a certain level. Or if the mass is already moving, this is the force you need to apply to make it stop if it is moving at a certain acceleration. So the mass and acceleration are already creating an internal force, and the xf is required either to stop it or to bring it to that level. So that's the equilibrium. So mass and acceleration are already a moving dynamic, and then the force, external force, is either required to bring it to that equilibrium or to stop it from and bring it to zero. And the important thing here, Newton's physics, is that the body is not there. It's just a mass. There is no body. And that is the key difference, that there is no body. It's just mass with no body, no physical thing. Because physical things will not be like this. They have physical properties, and they are not included here. Only mass is included. How can you have a mass without a physical body which can deform, which have K, which has many things? But Newton ignored all of that and said, okay, I don't care about that. I only care about the mass, which is obviously not possible. So this is one side of the physics. This guy, the other one, went completely the other way. He said, I don't care about the mass. I care about a structure, about a body which is fixed. And if I try to push it, it will deform. It will not stay. It will not move away. It is already fixed to the ground. So it cannot. So the first one is on the wheels. You just push it, it will run away. Frictionless wheels. No resistance of any kind. This one is saying, no, the body is actually fixed, but I want to move it. So if I move it, it will deform. The body will now have deformation, and that deformation is now proportional to the force, and the stiffness is the proportionality. So that means now we have a different look at the same thing. Mass is ignored, body is back, and now the force is proportional to stiffness. In one, the force is proportional to mass is constant, kind of, and acceleration. In this one, the stiffness is constant, kind of, and displacement or deformation is proportional to force. So two very different views of the thing, right? And then both are good in their own way, but one is static equilibrium and one is the bodies in motion, right? Once you combine them together, comes this combined equation. The body is trying to move like a free body, but you also hold it and the mass is also there. So now when you put these two equations together, you get this one, that because acceleration is changing with time, so you have a time now, the force required at any given time, because body is accelerating and it's also fixed, will now be as two equations, because F is here, you just add them together, you get this one. This is the beginning of the dynamic equilibrium of the system, that where we have the mass which is trying to move and already moving, but we block it. And now at any given time, because of the changing acceleration by definition is changing, that will be the force required. So now the force is no longer constant. Force is function of time, and it's linked to acceleration because acceleration is a displacement with time. Physically, you understand two very different things combined together into one complete system. So now the body cannot run away like a roller. It is bound. So that means the equilibrium must be established at every instance of the time until body stops moving or it's broken and runs away. Okay. So now we are talking of bodies which they're moving, but they are not leaving the ground. Okay. They're fixed to the ground and they're deforming as a result of the movement. Clear? Okay, displacement, as you know, u and acceleration are the same quantity, just one is unchanging, one is changing with time twice. Velocity is dot one and acceleration is 2 dots. Okay, derivative of time one time and derivative of time second time becomes acceleration. So that's the basic math here. So this becomes now our starting. This is engineer's view, that is the physics view, and then we have a combined view of the two when combined together. But this is still missing a very important parameter. What is it missing now? Damping, because it is saying that the body K is a stick which can deform without any material change, stress or strain inside. Because as soon as you have strain, you will have internal resistance from the material also coming up, which is different from the K. So that means damping will come in now. The damping is a property that the structure with molecules will change, the density will change, and heat will be generated when it moves. So all of that now comes in because that will also add another force into the system. So that means we go and we say, okay, now damping is also part of the column. Column is not a stick, column is real material. And when it deforms, it will have internal heat generation and internal change in its molecular compaction and so on and so forth. So the damping also comes in from the material of the structure and other things. So now we have a more complete equation where we have the mass and acceleration. Damping is related to velocity and stiffness related to u. So we have u dot, u double dot. We have now a complete system. We have the entire equilibrium system. So any force acting on the body has now 3 parts within the structure. One part coming from stiffness, displacement, one part coming from damping, velocity, one part coming from acceleration and mass. So which means total equilibrium. We don't know which one is which. We don't know the components. That's why this equation cannot be solved easily. Because first of all, u has the derivatives. Secondly, we don't know their individual contributions. And that's the problem. It has to be solved in different math ways, okay, which I'm not going to discuss. I'm hoping you did that in dynamics. And then we say, okay, the force this is not fixed. What if the ground is actually moving? Ground is also moving. So now we have another problem that previously the ground was fixed and the force was going to be generated as a restraint to the ground. So that was perfect. Now we say, no, the ground is also moving and the force is also there, right? So that means that force and plus the ground movement will now interact with each other. And now we have this equation where the force is actually the ground acceleration, which is also moving at the time. So you add that and then you create this equation. So this becomes the ground motion equation. So we have the physics equilibrium, you have the static equilibrium, you have a dynamic equilibrium for an applied force, and this is a dynamic equilibrium when the ground is moving, but there is no force applied as such. So, but the force will be now generated inside the structure. That force will be generated this right side, inside a stiffness force, damping force, and mass forces will be generated. And that will be equivalent. So which means now the motion will generate forces into the structure, which will be coming from this one. And that's exactly where the difference in earthquake and wind will be. Wind is going to be here, earthquake is going to be here, right? But this is so far, they are assuming that everything is linear because we started with Mr. Hook, who said it's linear. Like you said, it's proportional. But then when people start to observe physical things, they thought This equation came from him. They said, okay, it's fine. But when they tested the material or they tested the structures first time, like you did in your class, they found that no, the actual response is not linear. It is nonlinear. It doesn't go on forever. The beam did break. The beam start to behave linearly. And you observe that. So people observed that long time ago. They said, okay, Mr. Hooke's equation does not apply indefinitely. It needs to stop somewhere. The material has to break somewhere. Damage has to come in. This will break. It will not remain the same. It will crack. It will be damaged. Everything will change. Stiffness will change. Damping will change, and so on. So that real, and then this nonlinearity, people say, okay, we can't, the equation is good, but it's useless because real structure goes like that. Especially in earthquake damage was quite obvious, right? So they found that, okay, nonlinear for a given displacement, because displacement is the primary variable, you remember. So force is calculated from displacement, velocity, acceleration, or displacement based. So displacement, for a given displacement, we have the nonlinear force here and linear force over there. So it's quite clear that the linear equations is overestimating the force in this case, highly overestimating the force the structure can take. The structure cannot take that much force at that displacement. It has already broken down, already been damaged. So which means we have to correct now this, we have to make a correction. This is the known quantity that we have before from the previous equation, but the real quantity is here. So we have to make a correction, delta F, in the force, which is called the nonlinearity correction. So if we can find the delta F, then there will be great, because then we can find the blue line, correct? But the delta F depends on the blue line. So now we are in a serious problem because we are trying to find the blue line which does not exist. So delta F is unknown. We are trying to find delta F when we don't know where the blue line is. So which means that now we are in serious trouble, that nonlinear correction cannot be found unless we find it step by step, small errors, and keep correcting it early on through iterations until we make sure that this line is, basically we keep shifting our line until we follow that line. So that's the iterative procedure for finding that. So there's no jump that we can do like this, right? So now we add one more complexity to our problem. So we go back and we correct our force Ku plus delta F. Plus or minus doesn't matter. Sign is not important. Could be plus, could be negative. So that means the Hooke's equation of linearity needs to be now corrected for nonlinearity. And we make this correction and we go back and we add this correction here. So we say Hooke, new equation for nonlinear static response is Ku plus delta Fn, nonlinear correction, right? Then we combine this back to the dynamics. We make a nonlinear dynamic equation, equilibrium equation. We make this correction to the ground motion. We get the nonlinear ground motion equation. Now we have the full picture. We have the stiffness, we have the mass, we have the damping, and we also have the nonlinearity corrected. So which means we have now an equation for applied force, and we also have a ground motion, both complete nonlinear dynamic equilibrium equations, two of them. So which means the math is now there, right? How do we apply it? So that becomes our final equation for earthquake, for example. So now this is the situation. We have kind of a spring thing. We said this is mass, this is K and C. They are in series here together, acting together, the mass. This is our spring system. And we say, okay, we can write this equation for this one. And the nonlinear, so this is external force. That is the mass acceleration component of the force. That is the damping velocity component of the force. This is the stiffness displacement component of the force. And this is the nonlinearity correction, which again depends on this one, the whole, because the damping can be nonlinear, stiffness can be nonlinear, even the mass, although normally it doesn't change, but you can put that, the whole thing. So it becomes, so equation now needs to be solved by iteration, because this equation includes the equation. Okay, so that's the story behind the whole analysis. Once we have this equation, this is very good for one small spring. But as you know, structure is not one spring. It's thousands upon thousands of springs. This is 1 degree of freedom or one spring. But the structure is thousands upon thousands and millions or hundreds of thousands of degrees of freedom. So which means we need matrices. So now if we go to the structure, we convert these into mass matrix, damping matrix, stiffness matrix, and all of them matrix rather than individual single numbers. So they are now vectors having as many numbers as there are degrees of freedom for each one of them, right? And then we have the structure, and then now we have the nonlinearity, we have the time varying force over there, and you get this equation, and then you get the external force, mass acceleration for a structure now. So from the spring, we upgrade to the structure by using the matrix. Now the solution is even more complicated because these are all interconnected. So the matrix of the structure of everything, because each is a vector multiplied by vector, it would be a huge matrix, right? So that means solution now obviously becomes very, very hard in terms of finding that, and the stiffness and the interaction between various stiffnesses. So this is what all of the new software do. Solvers are developed to solve this equation. That's all they do. They solve this equation in the best way they can. And there's so much research on solvers, parse solver, that solver, skyline solver, because it's about the memory, it's about the speed, it's about everything. So now so much work has been done on solving these equations, almost saturated now at the point. Now people are thinking that can we use AI to solve this equation? Because AI is also the same thing. AI is nothing more than matrices, huge matrices with lots of numbers correlating with each other. So if we can use AI to do that, why can't we use AI here, right? So that's the next line of thinking, that instead of actually solving the equation, we can use AI to predict the response, right? Because the two are the same. Okay, so that's the knowns are mass, stiffness, damping, and force, and unknowns are the displacements. So which means to solve the structure now, we need these knowns to be defined, and that's the modeling part. We need to find out where's the mass, how to define the mass properly, we can't miss the mass, how to add stiffness, all of the stiffness. We talked about the stiffness the whole course last year, the material stiffness, the member stiffness, the structure stiffness, all the stiffnesses. So stiffness has to be built up from material all the way to structure, and we have to have the nonlinearity correction in the stiffness, and we have to find damping, and we have to find the force which varies with time. So all of that has to be found and defined first before we can solve the equation for displacement, velocity, and acceleration. Once we find displacement, we find velocity, and we find acceleration from there. Now, is everyone clear about the problem that we are solving and the input and output? So the modeling part is this, software's part is here. Software will do this, but you need this input, this data. So this data is your model. As good the model you have, the better results you will get here. If the data is not good, this result is also meaningless. So depending upon which data we have, we choose the part of the equation to be used. We don't have all the data all the time. We only have partial data. So based on the partial data, we use partial equation. And that's what we are discussing next. Okay, so that's the equation. Let's now analyze this equation one more time and look at various parts and see what we can get out of this one for earthquake analysis. Because I changed that equation from force to ground motion now for the time being. So because one of the important thing is earthquake analysis. This equation we can use for wind, and we will come back to it later. Because for wind, we can ignore some of the other things, and I will tell you later. Also, I already told you, but let's go here. So this is the earthquake thing. Okay, so if you take this equation and you delete everything and only keep mass and stiffness and delete all the other items from the equation, you will get this equation, which is the equation of eigenvalue problem. Eigenvalue, this is an eigenvalue problem. This is a mathematically speaking, it's an eigenvalue problem when you have two things equal to zero. And this is because you have two items and they're equal to zero. So for this to be zero, left side has to be zero also, but then which one of them will be set in such a way that they come out to be zero. So there are many solutions to that. Eigenvalue problem is that there are many possibilities in which either this is zero or that is zero or this is zero or this is zero, anything or any number, any possibility of combination of u and k and m and exploration can be made to be zero. Correct? Not one. So many combinations are possible, right? This is minus 10, this is positive 10, 0, and so on, right? So which means that this equation has no unique solution. It has many solutions, many possible solutions. That's the eigenvalue problem. So there are n number of solutions, and each solution has a certain value, and a corresponding detailed, if it's a vector, then it will have a corresponding whole vector available. For if it's a mass is a vector, k is a vector, then you will have a whole vector of solutions for each solution. So this is what we call the modal analysis, and we call it free vibration analysis. This is the natural response of the structure, because we have taken out everything which is not structure. We have taken out damping, we have taken out the applied force, and we have also taken out this is a structure at rest without deformation. So everything is taken out. It's just two things left now: mass and stiffness. Other things are taken out, and we have this interesting problem. This is called the natural response of the structure of free vibration. And today topic is about this one. Then we can say, okay, I will take out this one, force is equal to this one. I will have an equivalent static force. That means I will say that mass and acceleration is actually converted into an equivalent, because mass and acceleration is Newton force, right? So we can say, okay, I will replace that acceleration and mass by a force, because it's a force. And that becomes equivalent static analysis. And that's what people did all the time before the computers. They couldn't figure out how to calculate for earthquake forces. So they will just convert that into an equivalent force and apply at the floor. Still, the codes do that. They ask you to convert the structure into equivalent force applied at each floor, called equivalent static force for an earthquake, taking the mass and acceleration, multiplying them together. And that factor is mass by 10, mass by g by 10, g by 20, or something like that. The acceleration is assumed to be like that, multiplied by weight. So this is a very famous or simplistic way of converting this equation, ignoring everything and just converting the mass and stiffness in that way. Okay, so that's that one. Then you have response spectrum coming from there. We will talk about that. One form of the equation, you get response spectrum from the displacement. We will talk about that today. And then we have the pushover coming from there. We keep the nonlinearity, but we remove the mass, acceleration, and other things, and damping also. We just remove mass and damping, but we keep stiffness and nonlinearity. So by taking pieces of the equation, we get many methods of analysis. We can say linear time history. By ignoring the nonlinearity, we get linear time history from there. And we have the full nonlinear time history. So which means that from the same equation, by ignoring certain numbers for the data for which we don't have the data, we can carry out a simpler analysis. If we don't have the computers, we don't have the software, we just ignore things that we cannot do and make it as simple as we can and solve it. And that's what people have been doing. Equivalent static analysis is what people have been doing for centuries, right? Because we didn't have anything better than that. Now we have the tools to do the entire nonlinear time history analysis, and that's a problem. Actually, it's not a good thing. It's a bad thing, because now you have to do it, and you have to have so much data, so much understanding, so many tools, so much more work to do. When I started, no one can ask me to do nonlinear time history analysis because it doesn't exist. So all I have to do is I take the code, multiply the frame, I apply the frame horizontal load, G by 10, and do hand calculation by moment distribution. I'm done. By the end, nothing more can be done. I don't have any tools. Now you have all the tools. You have no excuse. So which means knowledge and understanding of doing this will be very important. Okay, so ignore nonlinearity, we get that. Natural response simplified with factors, ignore inertia, this one, and maximum linear response only, we get this one. So there is the summary of the analysis. Software now do the same thing. They give you analysis options. You pick one of the options from the analysis type, and they will ignore other things and run part of the equation. Everyone clear about this? Okay, so this will lead to now many things gradually. So we will take now one item at a time and talk about it. And I'm going to take the first one, modal response first, which is the most important part of the equation because it is the natural inherent response, does not depend on external forces, does not depend on anything else, just the mass and acceleration, just this body lying here untouched. What is it going to do if we just leave this phone here? You will say nothing. No, but actually that's not true. It's doing something all the time. It's vibrating all the time in its natural frequencies. And whatever I do to this one, its first natural instinct will be to respond according to its own natural frequencies first, right? And that's the key. So we have to know the natural tendency of the structure to respond, because that will be the first reaction from the structure when we disturb it. Okay. All right. So let's go there. So we take out everything. We just keep those two together. So we need a mass matrix. We need a stiffness matrix. And we take the U displacement and acceleration, and we make it equal to 0. Now we have to find all the possible ways this equation will be satisfied. And every possible way will lead us to a certain vector of deformations, means shape, the deformation shape. So each vector has, each solution will be one value, and that value, when you put there, will result in this to be 0, and also will lead to a set of, because it's a vector, so for each one have to be a combination together, not a single number. Whole vector has to go into that to make it 0. That vector is the one that we are going to use as a, so there are two things now called the natural frequency will come out of this, and a mode shape will come out of this, right? Mode shape is the vector of displacements, and frequency is the number or multiplier that will result in this to be 0. So that's an arbitrary number, not real. It's a scaling factor for those displacement that once multiplied will give us this equation to be 0, right? So that's the math behind that without going into the math. So known is M and K. All right. Unknown is the Ti and phi. So Ti is the natural frequencies, and the mode shapes will come out of that. The math is Not that complicated, but I'm not going to go into detail at all. Okay, so that's the equation, and read the red line. I will not go into the math of this, solving this equation, right? Not my job. I'm just going to use this for the structure and show you how we can apply it and use it. Okay, so we call it the heartbeat of the structure. It's the nature, because we are just leaving it alone. So if the structure is, structure is actually alive in a way. So that's the heartbeat. It's just vibrating at that natural frequency, or as we say, which is the heartbeat. And this depends on the stiffness and the mass relationship. If you change any of that, that heartbeat will change. If you don't change them, that heartbeat is constant. So which means we can find out now the heartbeat just like the pulse of the structure, right? And if the pulse changes, that means either you are sick, or that you are excited, or that you're not feeling well, you have fever. In a natural state, your pulse must remain constant. There's a certain resting pulse rate, as you all know, and everybody has that, So 65, this is all these trackers. If you have trackers, if you wear it, when you wake up in the morning, before you get up from the bed, lying still, that is your resting heart rate. Not doing anything, just lying. And your heart rate is your constant. And that should be, if a young man, fit young man, around 60, 65, older, as you get older, heart rate becomes faster and faster, right? Because the heart becomes weaker, so it has to pump faster. And very strong athletes, like super athletes, as low as 45 or 50. So because their heart is so strong, it only needs to beat slowly, right? So that's the next. So that tells you your health, how fit you are, right? Exactly the same thing for structures. The natural heartbeat, the heartbeat of the structure will tell you how good the structure is, right? So if you're a good doctor, you just put your hands on the pulse without a tracker, and you say, okay, the old doctors, the senior doctors still do that. They just check the pulse, and they say, oh, you have fever, or you have whatever, because from the pulse they can tell everything. It's not the rate; it's also many things there. So just remember that this is the exact same analogy. Heart rate of a human being and the natural frequency of the structure are very much correlated. All right. So this will tell us a lot of things about many of these things. So if we are able to measure this heart rate of the structure, then it will help you to assess the deformation, drift, acceleration, energy, damping, ductility indirectly. It will affect all these things. So that means if we know the heart rate, we will know where these things are going to go. So if we control the heart rate, which we can, then we will be able to control these things also, right? How can we control the heart rate for the structure? Because there are only two things, mass and stiffness. So if you want to control it, you either change the stiffness or you change the mass. There's the only two possibilities, right? For human beings, yeah, you exercise, you get fit, your heart rate will become better. Yeah. Okay.